Hello, everyone. Good morning, good afternoon, and good evening. My name is Eva Zadvorna. I'm Vice President and Director of Cultural Affairs at the Kościuszko Foundation. And on behalf of the Foundation's President, Marek Skulimowski, who needed to be in Poland today, I'd like to welcome our distinguished guests, Professor of Physics at Michigan State University and Warsaw University, a member of the Kościuszko Foundation Collegium of Eminent Scientists, and this event's honored guest, Professor Witold Nazarewicz, welcome. President of the Polish Institute of Arts and Sciences of America, Dr. Robert Blobaum, Kościuszko Foundation trustee, chair of the Foundation's Collegium of Eminent Scientists of Polish Origin and Ancestry, and also the chair of the Casimir Funk Natural Sciences Award Selection Committee at the Piazza, Dr. Hanna Chroboczek-Kerker, and the Foundation's longtime member, friend, and supporter, Dr. Norman Kerker. A big welcome to you all and to all our attendees who are joining us now here on Zoom from various places and from different time zones. As I mentioned, President Skulimowski is now in Poland, where he's performing and attending various of the Foundation's functions. And some of these functions include presenting Foundation's awards to young scientists in recognition of their achievements. And I'm referring here to the Witold Lipski Awards that were presented to computer science specialists last week, and the Frank Wilczek Award, recognizing achievements of young scientists in physics. And this award is going to be presented tomorrow. And today, here and now, in this virtual realm using Zoom technology, we would like to give recognition to an established scientist, a distinguished scientist, the scientist who has made a significant impact in his field of study, the impact that is reflected by the many prestigious honors and distinctions he received. We want to share information about his outstanding contributions to science with our Polish-American community and our constituency. That is the goal of the Collegium of Eminent Scientists of Polish Origin and Ancestry, which was established and has been operating under the umbrella of the Kościuszko Foundation. And trying to accomplish this goal, we're joining forces with the Institute of Arts and Sciences of America, which shares the Foundation's mission in that regard, and which award is going to be presented. And now I'd like to turn this podium over to Dr. Hanna Kerker to deliver her remarks. Thank you all very much.
Thank you, Eva. In the year 2012, the Kościuszko Foundation established the Collegium of Eminent Scientists of Polish Origin and Ancestry to recognize the accomplishments of Polish-American scientists. The Collegium was created by Dr. Zbigniew Darzyńkiewicz, a prominent scientist and a trustee of the Kościuszko Foundation. Dr. Darzyńkiewicz set out to create a prestigious organization of Polish-American scientists whose achievements deserve recognition. The organization was also created to provide a directory of eminent scientists they could serve to further contacts and exchange between the countries. The Collegium now numbers 453 members, and their number continues to grow. Among the members of the Collegium are 4 Nobel Prize laureates and many leaders from all areas of science. There are more than 30 distinguished physicists, and among them, this year's Funk Award recipient, Dr. Witold Nazarewicz, John Hanna Distinguished Professor of Physics at Michigan State University. I also have the honor to serve as the Polish Institute of Arts and Sciences of America, Piazza, chair of the Casimir Funk Natural Sciences Award Selection Committee. The Funk Award was established in 1995 and named for Casimir Funk, the discoverer of vitamins. Casimir Funk's pioneering findings had a great impact on science of nutrition and medicine. The award honors and recognizes an outstanding natural scientist of Polish origin. Among the 15 award recipients are 4 Nobel Prize laureates and other esteemed scientists. Today we add to the prestige of Casimir Funk Award by recognizing Professor Witold Nazarewicz, an outstanding physicist of Polish origin. Both the Kościuszko Foundation Collegium of Eminent Scientists and the Piazza Casimir Funk Natural Sciences Award helps to publicize the achievement of the illustrious members of the Polish-American scientific community. And today we recognize Professor Witold Nazarewicz.
Thank you very much. And now I would like to turn this podium over to Dr. Robert Blobom.
Thank you, Eva. First, allow me to thank the Kościuszko Foundation and its Collegium of Eminent Scientists for providing us this platform and for organizing today's lecture. This form of cooperation between the Kościuszko Foundation and the Polish Institute of Arts and Sciences is much appreciated and should serve as a model for our future joint endeavors. Nobody embodies this cooperation more than the chair of the Casimir Funk Award Committee, Dr. Hanna Kilker, to whom we owe this our sincere gratitude for her longstanding service in this capacity. So thank you, Hanna. As Hanna mentioned, Piazza established this award in 1995, the Casimir Funk Award, along with a number of other awards to recognize outstanding contributions in the humanities, the social sciences, the applied sciences, and the natural sciences, for which the Casimir Funk Award honors those who make outstanding contributions to that field. As she said, it honors an outstanding scientist of Polish origin, either Polish-born or Polish ancestry, living or working in North America. The nominee should have wide-ranging and major contributions to scientific research. And as Hanna said, it includes other recipients from the past have included 4 Nobel Prize winners. Roald Hoffmann in chemistry, Frank Wilczek in physics, Andrew Schally in medicine, and Jack Szostak in physiology or medicine. So joining this distinguished company of Funk Award winners is our 16th recipient, Dr. Witold Nazarewicz of Michigan State University. Dr. Nazarewicz, on behalf of Piazza's Board of Directors, we're sincerely honored to congratulate you in virtual person for your outstanding research contributions to the field of physics, and for your recognition as a 2021 Casimir Funk Award recipient. We're eager to learn more about your work in Designer Nuclei this afternoon. Now, to say more about the recipient is Dr. Norman Kilker. Norman, I turn it over to you.
Today we recognize Dr. Nazarewicz, and he is the chief scientist of the Facility for Rare Isotope Beams and a Hanna Distinguished Professor of Physics and Astronomy at Michigan State University. And as has been pointed out, he is a professor of physics at the University of Warsaw. Next slide, please. This is Michigan State University. In the honoring full disclosure, I have to say that Hanna and I are both proud alumni of the university. It enrolls 50,000 graduate, undergraduate, and professional students, and it's renowned for its agricultural school and its football and basketball teams, as well as many other good departments. Next slide, please. Oh, I apologize for this slide, but I was doing my research, I came across it. This is United States President Teddy Roosevelt giving an address at Michigan Agricultural College, which is now Michigan State University, in 1907. So I just threw that in there up for interest. Next slide, please. This is the Facility for Rare Isotope Beams. It's housed in a building on campus. It's not a very imposing building. It blends in among the other buildings on campus. It has no windows, but otherwise it's is fine. But if you look inside, the next slide, please. This is what you see. You see this mass of wires and cables and instruments, and you wonder how in the world is this all going to fit together to smash atoms and analyze the products. Hannah and I had a tour of the facility when it was under construction, and I had the same reaction. How does all this thing work together? Well, it does. And the next slide. This is a slide was taken during construction of the building. It has to be heavily protected from radiation, and so they poured in 3,600 cubic yards of concrete into the linear acceleration tunnel. Now, if you take a single cube of a cubic yard of concrete, that's 1 yard high, 1 yard wide, and 1 yard deep, and if you array them end to end, you would cover an area, a distance of 2 miles. So there's a lot of concrete in there. Next slide, please. Now, this came to in the email to me today that there is going to be a dance performance in the FRIB. So if you're in East Lansing on November 6th and you have $10, you can explore physics and dance with a focus on youth, women, and people of color. So it's providing other entertainment as well as science. Next slide, please. Well, what is the FRIB going to do? It's a scientific facility. I can't read all of it, but it's a scientific facility for the U.S. Department of Energy's Office of Science, and it will host the world's most powerful heavy ion accelerator, allowing scientists and researchers to access more than 1,000 new rare isotopes, with many never produced before on Earth. Scientists will investigate the makeup of atomic nuclei and how the universe formed, will drive innovation and fields like medicine, nuclear security, and environmental medicine. And that was from the university's president, Dr. Stanley. Next slide, please. What do we expect from the RIB? Well, we and everything around us are composed of atoms, and understanding the structure and properties of the atoms will give us a better understanding of matter in the universe and beyond. And the resulting knowledge will lead to advances in science and medicine. Next slide, please. The FRIB is an atom smasher designed to break atoms apart and analyze the resulting atomic structures, or isotopes. Understanding how these different types of atoms hang together and how they break apart helps scientists understand the laws that govern how all matter in the universe is put together. Next slide, please. Now, if you're a nuclear science dummy like me, I had to look up some things, and I want to make clear what an isotope is. This is on the left above is a atom of hydrogen. It has a single proton in the nucleus, P, and a single electron orbiting that nucleus. Deuterium, an isotope of hydrogen, has a single proton and the electron which orbits the nucleus, but it has an added neutron. So isotopes are essentially versions of the elements of the periodic table, atomic particles with the same number of protons, but a different number of neutrons. And Dr. Nazarewicz refers to this as his world as the Femtoworld, very, very small. Next slide, please. Michigan State's FRIB will provide researchers with the technical capabilities to study the properties of rare isotopes, short-lived atomic nuclei not previously found on Earth. Real-world applications include material science, we might read it, nuclear medicine, fundamental understanding of nuclear material, important to nuclear weapons stockpile caretaking, stewardship, and more than 20 working groups specializing in experimental equipment and scientific topics have been organized through the FRIB, a users organization. It's going to be a world center for people studying atomic nuclei. So next slide, please. So today we honored Dr. Nazarewicz, the chief scientist for the FRIB project. As pointed out, he received his PhD in physics at the Warsaw Institute of Technology, and then he stayed on in 1981 as assistant professor, associate professor, and then professor, and he left in 1991 to become a professor in the Department of Physics and Astronomy at the University of Tennessee, and he served as scientific director of the ion beam facility at the Oak Ridge National Laboratories, a huge center for a study of atoms and atomic nuclei. In 2012, he accepted positions as professor and scientific director of the FRIB facility at Michigan State, where he now works, and he has since been named to a university professorship. He has held numerous fellowships and visiting professorships around the world at the Niels Bohr Institute, Kyoto, the University of Cologne, and others. And his research has yielded 390 refereed publications with more than 20,000 citations, a huge number by any scientific standard. He participates in world meetings, scientific meetings all over the globe, and he has received acclaim and numerous prestigious honors. Among them, probably the most prestigious, he received the Outstanding Research Accomplishments Award from the American Physical Society, the Tom W. Bonner Award. He is a deserving candidate for the Funk Award. He has distinguished himself as an outstanding Polish scientist and a leader in exploring the fundamental properties of matter. And now is my pleasure and honor to turn the podium back to Dr. Robert Blobbaum, and he will carry on. Thank you very much.
Thank you, Norman. I believe that at this point, I probably should turn the podium over to Dr. Nazarewicz for his lecture. Again, Dr. Nazarewicz, thank you for appearing with us today, and congratulations on your receipt of the Casimir Funk Award for 2021.
Well, thank you very much for many kind words. Let me share the screen. So, can you see my screen?
Yes.
Yeah.
Oh, lovely. So, well, thanks so much for this very kind introduction. And I am very humbled by this award and by so many nice things which you said. And I must say, there will be very little for me to say after this great Norman's introduction to nuclear physics, but I will do my best. So if you come here to FRIB to see the dance, you won't see me there. Very good. So the idea behind this talk is to give a popular overview, kind of painted with a broad brush of nuclear science and nuclear science of FRIB. Okay, this is what I do. I'm a nuclear theorist, and I model nuclei, I try to understand them. So this is my menu. I will have some prelude, just general introduction. We'll discuss the territory where all nuclei live, and actually here in this slide, you see part of this territory, nuclear landscape. We'll talk a little bit about the role of nuclei in the cosmos. on how many nuclei an atom can and may exist. Norman was talking about applications, so I will mention something about applications as well, and then talk about FRIP facility and offer perspective. I'll try to be brief, and there will be no equations, no formula. It's supposed to be easy. All right. Usually I give acknowledgements at the end of the talk, but this time I would like to start from it. I would like to thank my family and collaborators and friends, because I owe them a great deal. I got actually interested in physics already at high school, at Lyceum, and I was very fortunate to have an amazing physics teacher who at the same time was a university professor. And then when I attended Warsaw University of Technology, Politechnika Warszawska, and Warsaw University, I also had outstanding mentors who became close friends and collaborators. And I am who am I because of my teachers. And I was also extremely fortunate to have extraordinary collaborators and students and postdocs. And they are all brilliant, curious, and innovative, and they love doing research. And this cartoon shows one of the ways we do research. And last but not least, I would like to thank my wife, Christina, for being patient with me and for supporting my passions. So this is an acknowledgement slide. So let me start from science. So I would like first to place the nucleus in the grand scheme of things. So this is a quantum ladder, which shows various objects which exist in the universe, starting from very small, going to very large. So this scale here is subatomic scale. Okay, those are the objects which are smaller than atom. And then you have macroscopic scale. So reduction arrow goes this way. So going in this direction, we reduce complex things into a smaller and smaller and smaller components until there is nothing to reduce. And when we go in this direction, we increase complexity of things, okay? So things are getting more complex. So what you see on this ladder, at the very top, there are galaxy clusters and galaxies and our Earth, stars and planets. So living organisms, main structures, and the humans, and cell materials. And here you see nanotube, because I'm talking about femto structures. So I had to mention nanostructures as well. And there are molecules and atoms. And atomic nuclei are more or less at the middle of the ladder. And this is a very fortunate position, because atomic nuclei are between very large and complex and very small and fundamental. So they can share many features with complex systems and many features with fundamental elementary systems. So below nuclei are baryons and mesons, protons and neutrons, which are constituents of nuclei, are baryons. And here you can see the proton. Proton is not fundamental at certain energy scale. Proton is actually a very complex system, which is made from even more fundamental objects, constituents, quarks and gluons. So what you see here are interacting quarks and gluons. So, and quarks are below proton and neutron, and below quarks and leptons are superstrings, perhaps, and then we don't know, okay? So this is where we are. This is where atomic nucleus is placed in the grand scheme of things, okay? So what is the time scale and distance scale of this science, okay? So this is time zero, this is Big Bang, and this is where we are. Is today is 13.8 billion years later after Big Bang. So Big Bang created extremely hot universe, 10 to the 12 Kelvin. After 10 to the minus 6 seconds, the universe was a quark gluon soup. And after 10 milliseconds after Big Bang, protons and neutrons were formed. So at this point, the basic constituents of atomic nuclei were formed, and then low mass nuclei were created, and neutral atoms, electrons were added, stars were formed, okay? The elements, various elements were created and dispersed over the universe. And this is where we are today. So the distance scale is from 10 to the minus 15 meters. So those femtometers, 1 femtometer is 10 to the minus 15 meters to 12 kilometers. And 12 kilometers is neutron star radius. Neutron stars are massive nuclei, okay? So in the National Academy Decadal Study Report, did this wonderful sentence, okay, that all the matter that makes up all the living organisms and ecosystems and planets and stars throughout every galaxy in universe is made of atoms, and 99.9% of the mass of all the atoms in the visible universe comes from the nuclei as their centers. So all attending this meeting are made 99.9% of nuclei. Okay? So the nucleus is actually a cluster made of protons and neutrons. In this diagram, protons are blue and neutrons are red. Okay, the nucleus sits at the middle of the atom, surrounded by atomic cloud. And the big questions which nuclear physics tries to answer, overarching questions, are how atomic nuclei are made and organized, where do atomic nuclei and elements come from? So what is the origin of atomic nuclei and elements? What are the fundamental particles and forces at work inside atomic nuclei? And what are nuclei good for? So these are basically overarching themes. So let me move this control bar here. I would like to talk about element transmutations, because what my field of nuclear physics does is it creates a new nuclei, new elements. So this is like modern alchemy. Alchemy was, we believe it was a pseudoscience, but it was a forerunner to chemistry. They manipulated, medieval alchemists manipulated materials. They developed basic techniques which are used in chemistry and metallurgy today, okay? And what you see here in this painting is an alchemist who is trying to produce the philosopher's stone, which was a substance, magic substance, capable of turning base metals such as mercury or lead into gold and silver. So alchemists were supposed to do basic transmutations of elements, okay? But more than 30 years ago, nuclear scientists at Lawrence Berkeley National Laboratory in California succeeded in producing tiny amounts of gold from bismuth, which is a metallic element adjacent to lead in the periodic table, okay? So in 1980, they ran an experiment in which they produced gold from bismuth. So the cost of running a beam at Berkeley was about $5,000 per hour, and they used a day of beam time. And as Glenn Seaborg, 1951 Nobel Prize laureate, said, it would cost more than $1 quadrillion per ounce to produce gold by this experiment. Okay, and the going rate for an ounce of gold at this time was $560. So this was not the very effective way of producing gold, but the gold was produced out of bismuth. So nuclear physics does things like this. In nuclear reactor, transmutations happen all the time. Okay, from heavy elements, lighter elements are produced. And many isotopes, we should not be horrified by this price tag here, because many isotopes which are obtained by nuclear transmutations are truly priceless. You cannot put a price tag on them. They are so unique that it's worth spending time producing them. So this is the nuclear territory, the grand nuclear landscape. This is the map which shows all isotopes, all nuclei which believes they exist. There are around 870 stable nuclei, stable isotopes, which are marked by black squares here. Those are stable, which means that they are not radioactive. This means that they surround us. They exist in nature, they exist in solar system. And everything which is not black squares here on this diagram are radioactive nuclei, that is, the nuclei which decay. And there are around 3,000 known to us, and there are around 7,000 nuclei which believe exist in nuclear landscape, okay? There are nuclei which have rather large excess of neutrons, and they exist on this side. There are nuclei which have many protons, too many protons to be stable. They're on the left-hand side, and here there are super heavy nuclei. Those are the nuclei which have very many protons and neutrons, and they are very heavy and they are very charged. And on the lower diagram here, shown is the neutron star. So you can view neutron star as a giant nucleus with 10 to the 57 neutrons. Is a very large nucleus indeed. So the goal of nuclear theories such as myself is to build a comprehensive model of the atomic nucleus, the model which will explain all those species in the landscape and will also explain neutron star. So let me start from the first topic about nuclei in the universe. So the big question is, how are atoms cooked in the cosmos? Okay, so new elements are produced in the cosmos all the time through the so-called nucleosynthesis. So there are reactions, transmutations which happen in the cosmos, which give rise to new elements. And this diagram shows the data. So this is the distribution of aluminum-26 along the galactic plane by searching for its radioactive decay. So aluminum-26 is a very long-lived nucleus. It lives almost 10 to the 6 years, and its decay, it emits a characteristic gamma ray with this energy. Then this gamma ray is detected by satellites orbiting laboratories like Comptel or Integral, and you can get the map of aluminum-26 in the universe. And there are regions in which there is a lot of aluminum-26, and there are regions where there is less. And this basically tells you about the rate in which aluminum is created and destroyed in those nuclear processes in the galaxy. So this shows that this process happens all the time. So this is an interesting periodic table because it shows the origin of every element which is known to us. Some elements, like hydrogen, helium, and lithium, were produced just in Big Bang. In fusion, resulting from Big Bang is called Big Bang nucleosynthesis. Some were created in the cosmic ray fission. Some were creating in explosive massive stars, such as supernova. And some were created in merging neutron stars. But you see that various elements were produced in different stellar environments. So the prescription in the cosmic kitchen for elements really changed from element to element. Okay, so this is a big challenge for nuclear physics and FRIB is to understand this pattern shown in this periodic table. So half of the neutron-rich atomic nuclei, heavier than iron, were created in the so-called neutron-driven R process. And the final abundances, that is the final amount of elements, reflect the structure of nuclei which were on the pathway of this R process. So here is the abundance of heavy elements created in this R process. And when I moved to Oak Ridge National Laboratory and University of Tennessee in 1991, so we all believe that all those elements were produced in supernova. But after quite recently, during last decade, now if you go on Wikipedia and look for nucleosynthesis, you will see that heavy elements are most likely, or most of those, were created in neutron star mergers. So neutron star mergers today is the massive merger of two neutron stars is the preferred site for the heavy elements. Okay, so on 17th of August 2017, a gravitational wave signal was observed by LIGO and Virgo gravitational wave detectors. Okay, so this was a collision of two spiraling neutron stars with a total mass of 282 solar masses. So here you have a nice movie which shows those two neutron stars spiraling, and they at some point merge, okay, after 100 seconds, and they send stuff out into the universe. They send new elements, okay, during this collision on this violent merger. And what you see, this blob here is a neutron star, heavy neutron star. Okay, in some of those collisions, black holes are created. I believe that actually in this particular event, it was a black hole. Okay, so the neutron star merger event, this particular one, given by this telephone code GW170817, resulted in so-called kilonova. This was a short gamma ray burst followed by optical afterglow, that is electromagnetic radiation, which contains information about heavy nuclei which were created in this event. And it is believed that a total of 16,000 times the mass of the Earth in heavy elements is believed to be formed in this particular neutron star merger, including approximately 10 Earth masses and just two elements of gold and platinum. So that's a very powerful way of creating gold for your ring. Okay, so one big question is to understand the nuclear matter on Earth and in the sky, in the cosmos. And a big quest for nuclear physicists is to understand the neutron star. Neutron star is a star which which has a size of 12 kilometers. Sorry, this is 12, and mass of 1.4 solar masses. So it's very heavy and fairly small. 12 kilometers is a really short distance. It's less than from East Lansing to Detroit. Okay, and neutron star, because it's so heavy, okay, has a very intriguing structure. Okay, so it has atmosphere which has around 10 centimeters, and it has envelope in which temperature changes dramatically. It has outer crust, which contains exotic neutron-rich nuclei, which are embedded in neutron gas. It has nuclear pasta in the inner crust, which is around 1 kilometer, which has fantasy phases, and like spaghetti, lasagna, etc. So it is pasta for good reason, okay? And there is outer core, which contains uniform neutron-rich matter. And what is in the inner core, we really don't know. It might be hypernuclei, it might be quarks, quark and gluon matter, okay? So we get information about neutron star by making direct observations, by measuring gravitational waves. So this is actually a LIGO detector, which measures those waves, and this is every facility. So we also carry out experiments to understand reactions with neutron-rich nuclei, and this gives us some information about neutron stars. So this is interesting scientific diagram, which shows on this axis the radius of the neutron neutron star, and then this is the radius of the neutrons in lead-208 nucleus minus radius of protons in the lead-208 nucleus. There are a little bit more. There are more neutrons than in protons, so neutrons are sticking out. So this skin is basically the difference between radii of proton, neutron, and proton distributions. And this diagram shows the correlation between this skin of lead-208, which is of the order of below of 1 femtometer, and the radius of the neutron star. And you can see there's a very beautiful relationship. So by measuring extremely light systems, small systems in femtoscale, we can get, perhaps through nuclear models, informations about so massive systems as neutron stars. Let me now talk about heavy. So I would like to say a few words about super heavy elements, okay, which are at the limit of mass and charge. So this diagram shows a way to produce super heavy elements. So calcium-48 beam is used, bombards californium nucleus. This creates the element with atomic number 118, okay? This element emits few neutrons and then decays down to lighter nuclei like livermorium, fluorovium, copernicium by emitting alpha particles. And copernicium eventually fissions, that is, it splits into two lighter fragments, okay? So this is how super heavy elements are produced in nuclear laboratories. So in 2016, 4 new elements produced in such reactions were added to the periodic table: organesson, OG, 118, tennessine, element 117, moscovium, element 115, and nihonium, element 113. There's no time to discuss their names. I would just add that tennessine, there was a contingent collaboration between Tennessee and Dubna laboratory in Russia, which has led to the discovery of element tennessine, and there was a strong Polish contingent involved actually in discovery of this element. So discovery of nihonium here was a great exercise in patience. Okay, they started this experiment, synthesis experiment, in 2003. So in between September 2003 and April 2005, only two events were discovered. Okay, so imagine you are a young scientist working on this experiment. You start in September 2003, okay, and it's October, November, there's nothing. But you still go to the lab and carry out, okay, and go on. And your patient is eventually rewarded. Element is produced, is added to the periodic table, and element is named nihonium for Japan. Okay, so things in this field take time. So just a short comment. Organeson belongs to the group. I'm sorry, let me go back. No, okay. Organeson formally belongs to the 18th group of the periodic table. So it is supposed to be a noble gas. So it's supposed to be an element which does not react, is not reactive. But theoretically, it is believed that organeson is a solid in normal conditions. It's not a gas. It's not a weakly reacting gas. It's normal. The boiling point for organeson is expected to be 325 Kelvin, 125 Fahrenheit, okay? It is expected to be a semiconductor in room temperature, and it is supposed to bind an electron. So it has a positive electron affinity, okay? Why is it so? Why is organeson so strange? Unlike its predecessors in the group 18, like radon, xenon, krypton, because its electrons are extremely relativistic. So since organeson has atomic number 118, the electrons in the inner shells of organeson move with velocities very close to velocity of light. And this changes its chemical properties. Okay, so this shows organeson in the group 18 in the full glory here. So this is period 7, which with the discovery of organeson has been completely finished, and group 18, okay? And the question is, where are the limits of the periodic table? How far can we go? Can we go to period 8? And can we add more isotopes of super heavy nuclei? Well, it is actually a very fascinating question, which is a challenge for the community experiment and theory. So chemists say that the element, we can talk about the element if it exists for at least 10 to the minus 14 seconds, because this is the time which takes the electrons to form a cloud around the nucleus. So 10 to the minus 14 seconds is the limit for atomic physics. Super heavy elements with super heavy nuclei with neutron numbers greater than 184 are expected to be short-lived because of primordial fission. From the nuclear physics point of view, they're expected to split into smaller nuclei. So it is very possible that when we get heavier and heavier in the nuclear landscape, the nuclei will have lifetimes which will be shorter than 10 to the minus 14 seconds. So we'll be still able to talk about nuclei, but those nuclei are not going to be atomic nuclei because there won't be any atoms. There will be nuclides without electrons, which means that at some point the chemistry will end, atomic physics will end. okay? Nuclei will still be there. Very short-lived, though. Okay, who cares? So Norman spent some time talking about possible applications of FRIP, okay? So what are the practical scientific uses of nuclei? So as you've heard, there are various practical applications, for instance, for FRIP, for medicine, for energy. Let me just show you one example which very nicely illustrates the role of rare isotopes in medicine, okay? So this is the example of targeted alpha therapy in vivo. Okay, so this is the experiment which was performed in CERN, in Isolde facility at CERN laboratory in Switzerland, but it beautifully illustrates the concept, okay? So the main culprit here is the main character, the good character, is 149 terbium. It is a nucleus, particular nucleus, which decays by emitting alpha particles, 17% of its time, okay? So it is unstable, it is radioactive, it emits alpha particles, and it has half-life of 4.1 hours. And this is very convenient, because if an isotope lives for several hours, it can be produced in the laboratory, and it can be transported to hospital, if hospital is not that far away. So in this particular case, the terbium was produced in CERN laboratory, and it was sent to Geneva hospital. Okay? And low energy alpha particles emitted by terbium have been shown to be extremely efficient in killing cells, in particular cancer cells. So the team here carried out an experiment in which 5 million of lymphoma cells, nasty stuff, were injected into mice. And 2 days later, the mice have been divided into 4 groups. The first group received no treatment. The second group received 5 micrograms of monoclonal antibody, rituximab, MOAB rituximab. So this is something which in principle is supposed to kill cancer, small amount. The control group C received 300 micrograms of MOAB, and group 4 got 5 megabecquerels of terbium-149. So they took this terbium produced in the laboratory and mixed this with antibody. So antibody has a wonderful feature, property, that it can detect cancer cells. So this is shown schematically here. Okay, my son is now my granddaughter, okay, they are great Lego admirers. So I could not resist myself making this graph. So you have this little ship, okay, which I called MOAB here. It takes terbium to the cancer, and then terbium sends alpha particles and kills the cancer. Okay, this is the way it works. Okay, so now the results of this experiment, okay, nothing, okay? Survival time is around 40 days. Okay, after 40 days, there is no mice alive. And then small amount of MOAB, okay, so chemotherapy, right, is here. We moved a little bit here. And then 300 micrograms of MOAB. Very good results, but unfortunate ending. And terbium-149, alpha emitter on MOAB, okay, fantastic outcome. So now you can see so what you can do with radioactive isotopes, which, you know, like alpha emitters, like beta emitters, okay? One needs to produce the right isotopes, which will have desired properties, which will produce alpha particles at desired range, which will have lifetime, which is practical. You do not want to have a radioactive isotope which will live for years, because then the patient will have to live with those isotopes, okay, for a long time, rather short-lived, but we are talking about days, and it should be, radiation should be proper range. Right, so let me finish the presentation with EFRIB. So EFRIB, as Norman said, will be the most powerful rare isotope research facility. This is unusual laboratory because it was founded by government. So this is US Department of Science, okay? So Department of Energy, so they kicked in $730 million, but the university also provided non-trivial contribution, and the state of Michigan. So three institutions, three donors, right? Sponsors, DOE, MSU, and state of Michigan, contributed to this facility. So this is a national, international user facility for world-class rare isotopes research, okay? So nuclear physics were present at MSU a long time ago. It started in 1958. And to add it to the list of accomplishments and to brag a little bit, something which Norman did not do, nuclear physics, MSU nuclear physics graduate program ranks #1 nationally, and I would claim also internationally. And here is the recent US News, right, and World Report, and this is the ranking of nuclear physics graduate schools in colleges. Michigan State University #1, MIT #2, Stony Brook #3, Berkeley #4. Okay, good result. So a short cartoon, short movie about EFRIB. Let me run it for you. It's really short, very schematic, but it will give you an idea about what EFRIB is.
Scientists study rare isotopes, the forms of elements that are not normally found in nature. They will be created at EFRIB using a 1,600-foot linear accelerator bent into segments and shaped like a paperclip. To create these rare isotopes, EFRIB researchers will start with a collection of stable atoms and move them through a gas of electrons where their electrons are removed, resulting in positively charged ions. Next, the positively charged ions are guided into the linear accelerator where they pass through each segment, gaining increasingly more speed and eventually reaching up to half the speed of light and directed toward a target. As the stream of ions strikes a target, the resulting collisions cause the ions to lose or gain neutrons or protons and become unstable, thus producing thousands of different types of rare isotopes, sometimes highly unstable and existing only fractions of a second. For what lasts merely fractions of a second, the rare isotopes continue to move through a series of magnets, filtering out the undesired types, leaving a pure beam with only the desired rare isotope. EFRIB has the unique capability to offer researchers fast, stopped, and reaccelerated beams, allowing experiments at the desired energy for all available rare isotopes. Scientists.
All right, so this is EFRIB, very quickly, of course, and this is what EFRIB will do. This is I'm coming back to my nuclear landscape plot. So this is where we are today. Those are the nuclei which are known to scientists. Many of those nuclei have unknown properties. So our knowledge is not as optimistic as is shown in this diagram, but at least those isotopes have been seen by scientists. EFRIB will significantly extend the current knowledge, okay, will double knowledge of known nuclei. It will access 80% of all isotopes predict to exist for elements below uranium, will extend the edge of nuclear landscape all the way to zirconium, and it will be also will give access to extremely neutron-rich isotopes, which are crucial for the R process, which exists somewhere here. Right, so it's time to wrap it up. So nuclear physicists do not want to just to observe every little nucleus in the nuclear landscape, because not every nucleus is interesting, right? Some nuclei are more important than others. So over the years, tremendous progress has been made in techniques to produce designer nuclei. Those are the nuclei which have characteristics adjusted to specific research needs and applications. So let me go back to this alchemist picture. So this is from the old book. This is medieval alchemist, and this person, he or she perhaps, is trying to cook new stuff here in the oven. But this is what nuclear physicists do. They produce designer nuclei, and some nuclei which are designer nuclei are shown here. So for instance, iron 45 is the nucleus which decays by emitting 2 protons, and you can catch it on the camera. Actually, in this experiment, Polish groups from University of Warsaw and Oak Ridge National Lab participated. They discovered this rare decay. Radium-225 is the nucleus which is believed to have this pear-like shape, is asymmetric. It looks like a pear. And this is the nucleus in which one can test why do we have more matter than antimatter in our universe. So this nucleus is important because of this question. Fluorine-18 and sodium-22 are important in astrophysics because they help us understanding novae events, okay? So orbiting satellites, such as this one, measure gamma rays associated with those isotopes, and nuclear physics helps understanding the signal. And terbium-149, I already discussed. You have no doubts that this is a very useful designer nucleus. So nuclear physics is a multidisciplinary field. It connects to cosmos. It connects to fundamental interactions, particle physics, cosmology, and it also strongly connects to complex systems, to atomic molecular physics, physics of open systems, condensed matter physics, emergent phenomena in atomic nuclei, material science, quantum chemistry. So this is a very rich, fascinating field. So let me finish with this analogy, okay? In my other life, I collect ancient maps. And when I started collecting, okay, when I started doing nuclear physics, nuclear structure physics was more or less like in this map by Münster, 1544. This is the map of the Americas. You can perhaps recognize South America, North America, this part of America, all the way to Grand Lakes was called Francisca. This belongs to French, okay? We still have some traces of French in Michigan, like Detroit, Detroit, right? So a very nice map. So things are more or less right, but not exactly. And then things were improving. This is like with nuclear physics. We're getting more and more complete picture. 1756, this is the map by Jolot Ottens, okay, French, Dutch cartographers, and you can see things are slowly converging. We can see the Great Lakes in the right place, okay? Things are yet to be desired here, okay? As you can see, California is still showed as an island. There was a period when California was considered to be an island, right? And this is 1822. Things are looking better, more precise. So this is Michigan territory, okay? When I show this map, I used to joke, and this will be understood by my North American colleagues, that this was the time when Michigan had two NFL football teams, one in Detroit and one in Green Bay, okay? As you can see that the map of Michigan is not as it is today, first of all, because of this, and then Toledo was still part of Michigan. Toledo was lost to Ohio in the so-called Toledo War. And this is how it is in reality, okay? And this is how we see atomic nuclei today. We see them with great precision, okay? This is, of course, from a satellite Google map picture. And we can, of course, still zoom in. So if Michigan is nucleus, then this picture of every laboratory looks like a structure of proton under a microscope with all these intriguing quark and gluon details, okay? So this is the map of diagram of FRIB, and this is why I'm giving this talk now. Okay, so this is my last slide. So we are traveling in nuclear physics, okay? Discovering new phenomena, trying to understand the structure of the nucleus. We want to understand the nucleus to know things and also to use things. And with this, I will finish the lecture. Thank you.
Thank you very much, Professor Nazarewicz, for this truly fascinating and very informative lecture, and this so powerfully and richly illustrated presentation that you shared with us. Thank you very much. To all our viewers who would like to rewatch this lecture once again, the recording of this webinar will shortly be streaming on our YouTube channel, which is Kościuszko TV. The best way is to subscribe, and then you'll receive notification each time we upload new video material there. And as always, we have some time for Q&A. Therefore, anyone who would like to ask a question to Professor Nazarewicz, make a comment, please do so now using Q&A feature.
Okay, very good.
I can see, yes.
I can see there are some questions. My answer to Julian Srebny. Julian, thank you very much. Okay. And then Jacek
says, congratulations from Warsaw. We are proud of you.
From Jacek Dobaczewski is asking, please tell us what is your dream future discovery of in nuclei. Well, I have great appetite, Jacek. I have short-term appetite and long-term. Short-term appetite would be discovery of calcium-70. It's a fascinating nucleus which can tell us a lot about nuclear models. And I would like us to go beyond organism, okay? So I can give you the whole list. Włodek Mandecki, how many stable nuclei might exist with half-life of at least 1 hour? They would be most useful for applications. Yes, indeed, they would be, but if they live for an hour, they are not stable. So there are 287 stable nuclei which exist around us, and they can be radioactive like plutonium or uranium, but their lifetimes are, longer than the lifetime of the universe. So we don't worry about this detail. Practically stable, okay? Lifetimes which are less than an hour, that I don't know. But you can go to NNDC website. So this is the website which is based at Brookhaven Laboratory, and you can just, in few clicks, plot all nuclei which live for time longer than 1 hour. Okay, so I cannot give you this answer right now, but you can, if you would like me to show you later, I would be very happy to do it, okay? By calling the neutron star nucleus, you add gravity to considerations. How do you calculate impact of gravity and other forces in such situations? Right, gravity, of course, is absolutely essential because neutron stars exist because of gravity, right? So the equations which we solve for neutron stars are relativist equations. They are general relative equations, but the essential input into those equations is the equation of state of the neutron matter, of the neutron matter. How the energy density depends on pressure in nuclear matter. So there's a nuclear physics component. So this is the big question for nuclear physicists. By using those general relative equations with nuclear physics input, we can calculate the radius and mass of neutron star and transport of neutrinos inside the neutron star and tidal polarizability, which is an important thing when neutron stars merge, etc. The next question, are there any other types of nuclei between usual nuclei, femtoscale, and neutron stars? This is a great question, okay? So your question is, do there exist any nuclei which are, say, between the neutron drip line, the edge of nuclear landscape, you know, and say neutron stars? We don't believe today, but who knows, okay? People are looking for such structures. For instance, this year, there was a paper produced on tetra neutron, on the nucleus, which could look like 4 neutrons. Nuclear theorists do not believe that such a structure exists, but this would not stop experimentalists from looking at systems like this. And there are, of course, proton emitters, like Aron 45, which I showed you in this beautiful photograph by Warsaw group, right? And this nucleus is formally unstable. It lives outside the nuclear landscape, okay? But we can manipulate it. So the answer to this question is partly yes and partly no. On the proton-rich side, we believe that there are such systems. On the neutron-rich side, probably I would not be so optimistic in finding an island of stability between neutron drip line and neutron star. And Krzysztof Rykaczewski just said, dear Witek, okay, thank you, Krzysztof. We are trying to address your dream right now with 551 vanadium beam on curium target, making Oak Ridge, running at RICAM, okay? In 3 years, you will get an event, and I will congratulate you, Krzysztof. I'm looking forward to it. That will be fantastic, okay? And now, Henrik Iwaniec. Henrik missed equations. But this is not my style, Henrik. What can I say?
I may have one question of general nature, referring to this beautiful painting by Frederick Edwin Church that you showed us as the last slide of your presentation. Could you elaborate, in your opinion, on the relation between arts and science? Are these completely two separate worlds, or do they combine? Do you use art to explain physics to your students?
I use art to explain physics. Well, I do not call my naive, slides, art, but this is very helpful. Okay, sometimes when I have some good idea, I go to professionals, to art designers, and I tell them what I have in mind, and they produce something beautiful, like the first slide introductory, slide with this beautiful three-dimensional nuclear landscape, where you can see those drip-line nuclei, which are neither bound nor unbound, forming a kind of vapor, right? I would not be able to do it, but I use this slide all the time, and it's very effective.
Professor Nazarewicz, we very much appreciate all the effort and the time that you gave us today. Thank you once again for this fascinating, very informative, great lecture. Thank you to Dr. Hanna and Dr. Norman Kelker for organizing and for being a driving force behind this event and all events that we presented as part of the Collegium of Eminent Scientists lecture series. Thank you to Dr. Robert Blobaum for collaboration and the opportunity to do this together. And also big thank you to everyone who joined us here today. Thank you for your great questions. And with that, I guess I would like to conclude this webinar, wishing you all a wonderful rest of the day and evening.
Well, thank you, Piazza, for organizing this event. It was fun. Thank you so much.
Thank you very much.
Thank you, Eva.